My name is 𝗨H𝗱𝗄𝗁𝗁𝗍𝗍. Welcome to Odessa Separator's webinar, Understanding the Mystery of Surface Dynamometer Cards. Today we will be discussing what dynamometer cards are and how they can be used to determine pumping system operating problems. Our discussion will include a basic understanding of beam pumped artificial lift systems and the various factors associated with them that can affect dynamometer cards. The purpose of this webinar is to show how dynamometer card interpretation can be a valuable tool for improving operating efficiency and greater operating profits. Keeping wells operating at peak efficiency is quite often costly, frustrating, and time-consuming in a pumping system that has been properly designed, assembled, and installed. Operating problems are the result of the nature of the fluids that are being produced and downhole conditions. The production of oil and gas is usually accompanied by water and various types of solids, either by themselves or in varying combinations. Depending on its composition, producing this mixture can result in poor pumping system efficiency, premature failure rates, excess energy consumption, and catastrophic equipment failures. Dynamometer surveys can be beneficial in determining operational problems and, more importantly, how to solve them. Producers and operators who take measures to determine operating problems and how to mitigate them as much as possible are going to have a far more profitable operation. So what is a dynamometer card? Dynamometer surveys produce dynamometer cards, which are simply a graphic representation of pumping system performance. A dynamometer card is a two-axis graph with the x-axis representing polish rod position and the y-axis representing polish rod load. The x-axis moves from left to right as the horse head of the pumping unit moves from the bottom of the stroke to the top of the stroke, or the upstroke. The x-axis moves from right to left as the horse head moves from the top of the stroke to the bottom of the stroke, or the downstroke. Pumping system load increases are represented by an upward movement of the y-axis, and load decreases are represented by a downward movement of the y-axis. Dynamometer analysis applies to beam pump, sucker rod artificial lift systems. These systems usually consist of a surface pumping unit, a sucker rod string, and a subsurface pump. The rod string operates in a wellbore with casing and tubing. The area between the casing and the tubing is called the annulus. The tubing string is filled with liquids and transports liquids to the surface one stroke at a time. The subsurface pump is a positive displacement pump that operates by means of pressure changes in the pump barrel. In general, a subsurface pump is comprised of a pump barrel, which is connected to the tubing string, a pump plunger, a traveling valve, and a standing valve. The traveling valve and pump plunger are connected to the rod string, which is attached to the surface pumping unit. The standing valve is attached to the tubing string. For purposes of describing how the subsurface pump works, let's assume for now that sucker rods do not stretch and that our pumping system is moving infinitely slowly. As mentioned earlier, the subsurface pump valves operate according to pressure changes in the pump barrel. Tubing pressure, noted as TP here, is a result of fluid in the tubing and will not change if the tubing is full. Annular pressure, noted as AP here, is a result of the fluid above the pump in the annulus and does not change for any individual pumping cycle. Pump barrel pressure, PBP here, changes from upstroke to downstroke to allow the pump valves to operate. So let's look at how a dynamometer card is created from the operation of the pumping system. At the bottom of the stroke, the rod string stops for an instant to transition from the downstroke to the upstroke. In other words, the upstroke is about to begin. The traveling valve ball, which had been unseated during the previous downstroke, falls onto its seat. Because the standing valve had been seated during the previous downstroke, the weight of the column of fluid in the tubing is being supported by the standing valve and the tubing string. At this point, the tubing pressure is equal to the pump barrel pressure, and that is greater than the annular pressure. The instant that the upstroke starts, the weight of the column of fluid in the tubing will seat the traveling valve. The system load, which had been supported by the tubing string, is assumed by the rod string. At this point, the tubing pressure is greater than the pump barrel pressure, which equalizes with the annular pressure. The standing valve ball unseats, allowing fluid from the annulus to fill the pump barrel as the pump plunger moves upward with the upstroke. The dynamometer card will record an immediate load increase or vertical movement at the polish rod. With the upward movement of the polish rod through the upstroke, the dynamometer card moves from left to right to the top of the stroke. At the top of the stroke, the pump plunger must stop for an instant for the system to transition to the downstroke. The standing valve ball falls onto its seat. The moment the pump plunger starts down, the standing valve ball seats. Because liquids are non-compressible, the traveling valve ball is forced off its seat by the liquids in the pump barrel. The pressure in the tubing string equalizes with the pressure in the pump barrel and is greater than the pressure in the annulus. With the traveling valve ball unseated, the pump plunger can now move down through the fluid in the pump barrel, which is contained by the seated standing valve. The dynamometer will record an instant immediate load decrease at the polish rod as the system load is assumed by the tubing string. Without pumping speed or rod stretch, the dynamometer card would look like the illustration on the left. Traveling valve seats, polish rod load increases, pump plunger moves up through the upstroke. Standing valve seats, polish rod load decreases, plunger moves down through the downstroke. To this point, we have been discussing a pumping system that is moving infinitely slowly and where the rod string does not stretch. In reality, rod strings do stretch, and that stretch has an effect on what the dynamometer card looks like. To this point, the pumping system will still be moving infinitely slowly. At the bottom of the stroke, the pump plunger stops for an instant to transition to the upstroke. The traveling valve ball falls onto its seat. The upstroke starts and the traveling valve ball seats. The rods begin to stretch as the system load is assumed by the rod string. The dynamometer card shows a gradual load increase at the polish rod. When the rods have stretched sufficiently to lift the system load, the pump plunger and the traveling valve can move upward through the upstroke. Fluid from the annulus can fill the pump barrel through the unseated standing valve as the pump plunger moves upward. At the top of the stroke, the pump plunger stops for an instant to transition to the downstroke. The standing valve ball falls onto its seat. The downstroke begins, and the fluid in the pump barrel forces the traveling valve ball off its seat. The standing valve ball seats the instant that the traveling valve ball unseats. The system load is assumed by the tubing string. The rod string relaxes an amount equal to the amount it stretched during the upstroke. The dynamometer card shows a gradual load decrease as the rods relax. When the rods have fully relaxed, the pump plunger and the traveling valve can move down through the fluid in the pump barrel contained by the seated standing valve. The diagram on the right shows the dynamometer card with rod stretch. Traveling valve seats, the rods stretch, pump plunger moves up. Standing valve seats, rods relax, pump plunger moves down. Thus far, the discussion has ignored the effects of pumping speed on what the dynamometer card looks like. Pumping speed affects the shape of a dynamometer card more and more dramatically as pumping speeds increase. To illustrate the effects of pumping speed on a dynamometer card, we will use a simple lever system with a spring, a scale, and a 10-pound weight. The lever system represents the pumping unit. The spring represents the rod string. The scale represents a dynamometer, and the 10-pound load represents the system load. The diagram on the left shows the lever system at rest with the scale indicating 0 pounds. As the lever is raised very slowly for the upstroke, the spring begins to stretch and the scale indicates an increase in load. Note that the weight does not move upward until the scale indicates 10 pounds. When the scale indicates 10 pounds, the weight will be lifted upward with the movement of the lever. As the lever is lowered very slowly for the downstroke, the scale indicates 10 pounds until the weight is fully supported by the ground. As the spring relaxes, the scale indicates a load decrease from 10 pounds back to 0 pounds. The dynamometer card shows the effects of the stretch. The lever is raised and the spring stretches to 10 pounds. The weight is lifted. The lever is moved on up to the top of the stroke. The lever is lowered. The spring relaxes. The lever is lowered to the bottom of the stroke. If the lever is raised rapidly, the scale indicates that lifting the 10-pound load requires stretching the spring past the 10-pound mark. Then as the weight begins to catch up with the lever, the spring relaxes while the scale indicates a load decrease. Stopping the lever at the top of the stroke allows the spring and the weight to oscillate, and the rod string alternately stretches and relaxes. The scale indicates load increases and decreases during this oscillation. Rod strings oscillate at a frequency that is fundamental to the rod string makeup. Furthermore, rod string oscillation adds to or subtracts from system loads during the stroke. The oscillation takes the form of a sine wave, and effects on the dynamometer card are illustrated in the diagram on the left. The lever is rapidly raised, the spring stretches, the weight is lifted somewhere past the 10-pound scale mark. The lever is stopped, the weight catches up, the scale indicates load decrease, the weight falls back, the scale indicates load increase, and through to the top of the stroke. When the lever is rapidly lowered, the rod string relaxes an amount equal to the amount it stretched during the upstroke. The rods alternately relax and stretch with similar equivalent effects on the downstroke. Combining these two figures produces a very good approximation of a surface dynamometer card for a properly operating well with a full pump barrel. In conclusion, the shape of a surface dynamometer card is a result of rod stretch in relation to pumping speed. In the next dynamometer webinar, we will discuss how operating problems affect the shape of both surface and downhole dynamometer cards and the correlation between the two. Thank you for taking the time to join us today. My contact information is on the screen. If you have any questions or comments, please feel free to contact me.